Hi, I'm Firdaus. Ever wondered what ordinary differential equations are, how they work, and how they are used in real-world applications? Well, worry not, because all your questions regarding ODEs will be explained in this video. In this video, we'll go through the fundamentals of ODEs, the methods to solve ODEs, and application of ODE in the automotive industry. Alright, so starting off with fundamentals of ODEs, we'll start with what is an ODE, as well as how many ODEs are there. So, by definition, an ODE consists of one or more derivatives of one or more unknown functions, dependent variables, with respect to a single independent variable. As you can see over here, we have an unknown function where we have the dependent variable on the left-hand side and independent variable on the right-hand side. As demonstrated below, here are the examples with two main notations, mainly Leibniz notation and Primes notation. Over here we have two unknown functions, and over here we have one unknown function. Now, as said in the previous slide, there are two notations for the derivatives, which are the Leibniz notation, dy dx, and Primes notation, y prime. I will not go into detail, but you may pause the video and read through to compare them. So now that we've finished what an ODE is, let's move on to the categorization. We'll be going through all these ODEs that are presented in this chart over here, starting off with the first order ODE, proceeding with the second order ODE. The first order ODE are split into the branches down here, and the second ODE are split into the non-homogeneous linear and homogeneous linear. Do not worry if this overwhelms you. We'll go through each of it one by one together. So let's start with the first order ODE. First order ODEs are equations that only have the first derivative y prime or dy dx, and they can be written in two forms such as the explicit form and the implicit form. Here are examples of the explicit form, and here is an example of the implicit form. Next, we have a separable first order ODE where f equals to u, a function of x only, and v, a function of y only. This equation is presented like this, and then it can be rearranged and separated like this, and then finally solving it by integrating both sides. Now we have non-separable first order ODEs. Contrary to separable ODEs, these cannot be separated and cannot be rewritten like this, hence it cannot be solved by direct integration. So what do? We reduce it to separable form only if it's homogeneous, and then we solve by integration as usual. Now let's compare the homogeneity of first order ODE, where we have the homogeneous and non-homogeneous. Homogeneous means lambda is of the same degree. As over here you can see lambda is times the x and y, and when you factorize it out, the degree of lambda is 2. Whereas for this equation, which is non-homogeneous, lambda is to the degree of 2 and also to the degree of 3, which are not the same, therefore it's non-homogeneous. For this part, we must test for the exactness of the ODE. Usually it's written in this form or this form. So we must find the partial derivatives of partial m over partial y and partial n over partial x. And if they both equate to each other, then it is an exact differential equation. Down here, you can see an example. As you can see, when m is derived in terms of y, we get 3x, and when we derive n in terms of x, we get also 3x. So this is an exact ODE. If they do not equate to each other, then it is not an exact ODE. Now let's compare a linear ODE and a nonlinear first order ODE. A linear one can be written in this form, whereas a nonlinear one cannot be written in this form. Also, a linear ODE has a maximum degree of 1, whereas this rule does not apply for nonlinear. Over on here, we have an example of linear, and here we have example of nonlinear. For a homogeneous linear first order ODE, Rx equals to 0, and for a non-homogeneous linear first ODE, Rx is not equal to 0. Over here is an example for homogeneous, and over here is an example for non-homogeneous. This non-homogeneous is also non-exact because partial m partial y does not equal to partial n partial x. And now we've reached Bernoulli's equation. So in this section, we're going to take a look at it in this form, where px and qx are the continuous functions on the interval we're working on, and n is a real number. If n is not equal to 0 or 1, then it becomes y prime plus pxy equals to, this is q, sorry, y to the power of n. It seems that this is a non-linear first order ODE. So to change to a linear form, first we divide both sides of the equation by y to the power of n. Then we let u equals to y to the power of 1 minus n. And then we differentiate u to get u prime and rearrange, and finally substituting equation 3 and equation 2 into equation 1. So we have a linear form of Bernoulli's equation, and now we can solve for u. And now we've reached the linear second order ODE, as can be seen presented in this form. We'll focus on the homogeneous and the non-homogeneous linear second order ODE only. Alright, so let's compare the homogeneity of linear second order ODE. On the left hand side we have homogeneous, and on the right hand side we have non-homogeneous. It's just that for homogeneous Rx is equals to 0, and non-homogeneous Rx is not equals to 0. We also have non-constant coefficient linear second order ODE, where Px and Qx are variables, and constant coefficient linear second order ODE, where A and B are constants. Okay, great. So now that we've finished the types of ODE, let's move on to the methods to solve these ODEs. We'll start with the first order ODE, and then we'll go to the second order ODE. Alright, let's go. So for solving first order ODE, we'll go through the non-separable and homogeneous, and then go through the exactness, and then finally the linearity. So now we'll be going to solving non-separable and homogeneous first order ODE. As you can see over here, we have an example. You can pause the video to see the steps, but basically we let y equals to vx, and then we separate the variables, and then we integrate both sides to get the solution at the end. So this is how we solve exact ODEs for first order. So the first step is to integrate du dx to get m dx to get u over here, as you can see, and then we take du dy and equate it to n. From here we equate it to n to get our k prime y, and then after that we just integrate k prime y to get our ky, and we substitute ky into the equation. Alright, so we have the example over here. So the given equation is over here. I will not go into detail, but there are mainly 4 steps, and the first step is to test for exactness. Second step is to find a general solution. The third step is to find k prime y, and actually ky as well. And then finally we substitute ky into uxy, and then we get the equation over here. Next we have solving non-exact ODEs. It's actually just like solving an exact ODE, but first we need to find the integrating factor, then reduce it to an exact ODE. So how do we find the integrating factor? With these 3 steps over here. Here's an example of solving non-exact ODEs given equation y dx minus x dy. So when we test it, it is indeed non-exact because partial m over partial y does not equal to partial n over partial x. So we have to introduce fx. So once we do that, we find the integrating factor of 1 over x squared, and we multiply the integrating factor to the original equation to get it to be reduced. And once it's reduced, we just solve it as a normal exact ODE, and hence getting the solution over here. So this is solving homogeneous linear ODE first order. So we just solve it by separation method, and then finally integrating both sides. For solving non-homogeneous, we have to rewrite into implicit form and then test for exactness. If it's exact, we can solve the exact ODE as usual. So we finished the methods to solve first order ODE. Let's move on to second order ODE. So for solving second order ODE, we have homogeneous with a constant coefficient and non-homogeneous with an unknown coefficient. And here's how you would solve a homogeneous second order ODE with constant coefficients. So the steps are written over here. So for the non-homogeneous part, basically we just have to find the complementary solution and also the particular solution. The steps are in here, I've written. For the particular solution, we find ypx based on this table over here, as well as based on this rule over here, the 3 rules. And once we've done that, once we've gotten the particular solution, we just add up the particular solution and the complementary solution together to get the answer. And now we've reached the last part, which is applying the ODE in the automotive industry. So more specifically, we'll go into suspensions. I will not go into detail as I do not have enough time, but you may pause the video if you wish to know what a car suspension is. And this is how a car suspension works. Basically, it stores energy that is generated when the car goes through a bump, and it also stores energy by compressing its size, thus making any type of force into energy And there are factors that affect the amount of energy of a spring can hold, which are the length, material of the spring, and also the coefficient of the spring. Here's brief information on damping oscillations if you wish to know more. So now we've got into the application of ODE. Basically, like the spring, the force is always opposing the motion of the mass. So with the damp system, the mass has now two opposing forces. So firstly, we have the force of spring, which is the negative k times y following Hooke's law. And secondly, the force of fluid is equals to this. So these forces are shown in blue in figure 2 over here. Again, by Newton's second law, the resultant force on an object is equal to its mass times by its acceleration, F equals to ma. So hence we get this equation over here. So expressing acceleration as the second time derivative of displacement, we can rearrange the equation into a second order homogeneous linear ODE with constant coefficients, as you can see over here. And we can find the roots of this equation by using this formula. This is the most simplified. Okay, and hence we have three cases for the damping. We have case 1 where c square is less than 4 times the mass times the coefficient of the spring under damping. Case 2, c square equals to 4 mk critical damping, and case 3 where c square is more than 4 mk over damping. Alright, so here's an example of a case 1 under damping. So we've given the parameters over here and we sub in the values for mc and k into equation 2, hence yielding this equation. This is a simplified equation. The characteristic for this equation is as presented, and the roots for this characteristic equation is also presented over here. And as you can see, it is a complex conjugate root, so the general solution is as such. Great, so now that we have the general solution, let's find the particular solution. So we find this by applying the initial displacement condition to find our first constant as such. And we find the second constant by deriving this equation over here. And our derivative for that equation is as such. And now we apply the initial velocity to the equation over here and find our second constant, which is presented as such. Hence, the particular solution is solved. So we turn the particular solution into an amplitude phase shift solution so we can easily plot it into the graph. So when we plot it into the graph, you can see it over here that this is the behavior for under damping. So as seen from the graph, the motion attenuates quickly after two oscillations. And the peak of the second oscillation, a mere fraction of the amplitude of the first. Although the oscillations are damped out quickly, this is still a case of under damping. So what happens when the damping coefficient is lowered to 150? So following from the steps in the previous slides, we finally get the particular solution of over here. We have find a particular solution of this as such, and when we convert it to amplitude phase shift to easily plot it into the graph, we get this graph, and I will explain this graph in the next slide. So based on this graph, there are at least 6 oscillations before the motion flattens. It seems that this car suspension performance is not that efficient. This is because the car is not stable and would bounce excessively at the slightest disturbance. An efficient suspension would be a critical damping oscillation where C minus 4 mk equals to 0, where m is the mass and k is the spring coefficient and c is the damping coefficient. This is because the car will not bounce excessively like an underdamped spring suspension, and the traction will not suffer as an overdamped spring suspension. Alright, so we have reached the end of my video presentation. I hope you've learned something new, and I hope you can apply ODE into real life applications. Thank you very much.